kids. So here it is. The quiz tomorrow is on electrons and waves and particles and such. Oh, are particles and waves. That, by the way, is my eggplant sandwich that people made fun of me today during the PSAT. That is eggplant. That is roasted red pepper. That is fresh mozzarella. And in there as well, that here, that's balsamic glaze. It's good stuff. Try it out. All right, so we talked about waves. You should know this already, that a wave is measured sort of from peak to peak. So an entire wave is the up part and the down part, as many of you have said. So that there is two waves. There's the crest, which is the higher part, and a trough, which is the lower part. The amplitude is as high above the median there that it gets. Here is an ocean wave to show you the equivalent. All right, and we talked about how everything here on this spectrum goes the speed of light. That's 3 times 10 to the 8th meters per second. So radio waves or microwaves or infrared rays, all of these go at the speed of light. This visible light here falls in here between 10 to the minus 6 and 10 to the minus 7. And so it's a very small portion of the whole thing, but we blow it up so that you know that red actually has a longer wavelength than violet, which has a shorter wavelength. And you can see that ultraviolet is on the violet side of things and infrared is on the red side of things. So you will have that if you ever have a quiz or test. So frequency and distance, we learned have an inverse relationship when we were doing the shooting hoops in the room. The further away the person was from the basketball hoop, the less frequent their shots were. If they got closer, they could rebound easier and get more shots off. So that frequency and distance, the number of shots they took and the distance they were, had an inverse relationship. The further they were, the less frequently they could do things. Waves and frequency, wavelength and frequency, have a similar inverse relationship because they're equal to a constant, which is the speed of light. And since anytime anything's equal to a constant like that, if one goes up, the other one's going to go down. That's a mathematic equation. So here, if they're going to equal this constant c, the wavelength, and the frequency, here, so the wavelength and the frequency, if these two things are going to equal this constant, 3 times 10 to the 8th meters per second, then if this one gets larger, this one has to get smaller so they can still equal the same number. And you might want to jot some numbers down to see if that's true. If you're trying to make things equal 4, and you had 2 times 2, they'd be equal, right? So if we want to make this one 4, that went up, this one's going to go down to 1. So as one goes up, the other one goes down if they're going to equal a constant. Anyway, that is neither here nor there. Wavelength for this to work has to be measured in meters because the speed of light is in meters and frequency is in hertz or waves per second. So that's why there's the seconds on the bottom here. So meters times hertz, which is 1 over seconds, equals meters per second. And that is that relationship. And then we also talked about if you saw trucks on the highway and little cars on the highway going the same speed, the frequency of seeing little cars bumper to bumper would be more than the frequency of seeing trucks, because this would be like trucks. So every now and again a truck would go by, but the little buggy cars would, because they're not as long as a truck, come by more frequently, even if they're going the same speed. And that's the situation. So relationships with electromagnetic spectrum. Energy and frequency also now have a relationship, but in this case it's direct. So the more frequent a wave is, the more energy it has. So as one goes up, the other goes up, and here it's graphically represented. Here's on the orange line, we're seeing the frequency. So as the frequency is going up from here to here to here to here, you can see the energy corresponding to that also goes up. And that's not surprising because we talked about if you're here on this side of things and then your friend is out here drowning in the ocean, help me, right? That's little lines of excitement because he's waving because he's underwater, right? If you had to get there to him, you would much prefer an ocean like this in an ocean like this, where the waves are just going to keep knocking you back over and over and over again. These waves are less frequent, so they're not going to hit you back as often. So it takes more energy to reach them here because these waves are pushing you back more frequently. So higher frequency, higher energy. Hopefully that makes sense. All right. And of course, you save them and it wins. All right. So here's an example of what we'll be doing as well. So an excited sodium emits radiation having a wavelength of 589 nanometers. The first question is, what is the wavelength in meters? Why is that important? Because in order for this to work, because the speed of light is in meters per second, your wavelength has to be in meters. So we're trying to train you to remember that. So what is the wavelength in meters? We have 589 nanometers. We got to convert that to meters. And you might remember from when we were doing this a couple of units ago that nanometers to meters, nanometers, nano is a 9. And it takes a lot of these to equal 1 meter. There's a lot of nanometers in 1 meter. And nano means small, so it's a bunch of these need to make one of those. So it's 10 to the 9th of these equal one of those. When you multiply the tops and divide by the bottom, you get 5.89 times 10 to the minus 7 meters. Number 2, what region of the spectrum are these atoms in? So then we go back to this thing, which you have, and it's 5.89 times 10 to the minus 7. So if you first look at your magnitude here, you would see 10 to the minus 7 is over here. And then that brings you down to the visible light region. And 5.8, I believe is what it was, 5.89. So it's less than 7, it's less than 6, it's less than 5.9, but greater than 5.7. So 5.89 would be like literally like almost at 5.9. So it's a yellow light. So that's how you read that. And we get that it is a yellow visible light that you see. Now, what is the frequency of this light? So now we're going to use this relationship. This speed of light equals wavelength times frequency. And the speed of light is 3 times 10 to the 8th meters per second. We now have converted our wavelength to meters, so we can put that in as meters, 5.89 times 10 to the minus 7. And we're looking for our frequency V. So this is basically like a number equals a number times X. And since this is a multiplication function, we're going to need to divide both sides by the 5.89. So you divide 3 times 10 to the 8th by 5.89 times 10 to the minus 7, and you get your answer, which is 5.09 times 10 to the 14th hertz. Remember the units here are hertz, which is 1 over seconds. We have 3 significant digits because this has 3 significant digits. 589 had 3 significant digits. This is a definition, the 3 times 10 to the 8th, so that is not what we use to determine our significant digits. That's considered infinite. So another thing to notice is that whenever you do this equation, right, the 3 times 10 to the 8th is always going to be on the top because you're either going to divide by the wavelength or the frequency. Let's see that in action here. So microwaves have a frequency of 2.5 times 10 to the 9th hertz. What is the wavelength? So again, we're using this equation, which is that the speed of light, 3 times 10 to the 8th. Ooh, Mr. Roach, not good. Hold on a second, kids. That should be a superscript H. I'm going to discard my wonderful picture. Hold on a second. All right. That was just some editing music. Superscript. Bam. All right. From current slide. Oops. From current slide. Here we go. All right. So, speed of light, C, 3 times 10 to the 8th meters per second equals the wavelength, which we don't know. That's what it's asking for, times the frequency, which we do know, 2.5 times 10 to the 9th hertz. No need to do anything with this. It's in hertz. It needs to be in hertz, so that's good. When we solve for this, we're going to take the 3 times 10 to the 8th and divide it by 2.5 times 10 to the 9th. The answer will be in meters because this is meters per second, and that's per seconds. So when we're finished, we get 0.12 meters. That is all I'm going to cover right now because that's all you need to know right now for your quiz tomorrow. And Mr. Roach needs a nap. So that's what keeps Mr. Roach going.